Hi, I'm Sammy. I'm the CEO of Eventual, and I drink espresso with a splash of almond milk.
Welcome back to another MLOps community podcast. I am your host, Demetrios, and today I am flying solo for the once in a blue moon times that I do this. I got the pleasure of talking to Sammy Sidhu. This was an incredible podcast. We go through all of Sammy's history. It was an incredible stint that he went through in the autonomous driving, autonomous vehicle era. And he went through actually 2 acquisitions of these startups that got bought out by bigger companies. The first one got bought by Tesla, and then the second one got bought by Toyota. And everything that he learned from that time doing this very low-level stuff with tinyML and optimizing, distilling these models, really making things work fast and work reliably, he put into his new company, Eventual, and Eventual has a offering that is open source, and I encourage anyone to check it out. It's called Daft. We'll leave the link in the description to that for anyone who wants to look at it. And let's just jump into this conversation with him, because I think you all are going to love what he talks about when it comes to the future of LLMs and machine learning and just data and how we store the data, how we query the data. Especially his specialty has been the unstructured data world and what he likes to refer to as the complex data world, and how you can make that much easier than just having some metadata that points to an S3 bucket. And that's really what they're trying to do at Daft. From my understanding of it, it's much faster and it's much easier and it's much more robust. So let's jump into the conversation with Sammy right now. By the way, if you enjoy this, it would mean the world to me if you send this episode to one friend so they can share in this joy with all of us. Let's get into it. Here's Sammy Sidhu. Talk to you soon. Sammy, great to have you here. Of course, you didn't think you were going to come on here without me talking about California raisins, huh?
No, that is true. I'm Sammy. I grew up on a raisin farm, and now I work in complex data.
Not just any raisin farm, though. Let's talk about this, because there's a lot of people probably that are listening that don't understand the cultural significance of the raisin farm that you grew up on, which is, I'm pretty sure a lot of millennials and people our age had your raisins in their lunchbox at lunchtime, and it was just a little box of raisins that probably came with like 20 raisins, and they said on the box, I remember distinctly, right? It was this small box, I think it was red, and it said California raisins on them.
It is. So I grew up on a farm that was one of the producers for Sun-made raisins, and the box, I think, is visible to most people, where it's the lady putting the tray of raisins out into the sun.
That was it.
And that's exactly what we did. We would grow grapes on a vineyard and cut them down and then make them into raisins. And the cool thing is that, like, no matter where I go in the world, I always am connecting with people over Sun-made raisins. I was in Korea for a conference, and I mentioned it at a dinner, and everyone's like, oh, I had that all the time as a little kid too.
Oh, wait.
So it's always something that connects with people.
They monopolized the raisin industry, huh?
No, it's interesting because it's actually a cooperative. So there's actually a bunch of farms in California that get together and sell the raisins together.
Oh, so what is the process of creating raisins? I know it's dried grapes, right?
It's dried grapes. But the thing with sun-made raisins is that it's made by the sun. So generally what you do is you have table grapes that you grow on a vineyard. And then what you end up doing is when they're ripe, when the sugar level is a certain level, you cut them down from the vine and you throw it on a piece of paper on the ground. And then what you end up doing is you kind of just like rotate it every few days until it's into raisins, and then you throw it into a big hopper.
So you grew up doing that. You would know when the raisin season was and when the harvest was and all that. And I imagine you were cutting stuff down?
Yeah, my parents put me to work. So my summers were cutting raisins and rebuilding tractors.
So how did that take you into complex data? What the hell was that trajectory like?
Yeah, it's a good one. Let's see. growing up on a farm, I obviously liked getting my hands dirty. So I worked on a lot of tractors with my dad, um, fixed everything around the farm, and got into like electronics and computers very early because of that.
Mm.
Um, my parents noticed this and got me out of the farm because, I was pretty much doing nothing at school at that point in the Central Valley. And so I moved to the Bay Area. And over here, I just got hooked on computers. Ended up staying local, going to Berkeley, and ended up focusing a lot on high performance computing, low level programming stuff, and then get bit by the math bug. I got into machine learning, and my professor, who I worked under in college, started a company. And that company worked essentially on building Autopilot for everyone else. And I ended up being the first hire there and eventually the CTO. And that's
Wow.
kind of how my journey got started. Working
Wait,
from... Yeah.
You said autopilot for everyone else. What does that mean?
Yeah. Well, at the time, what we were trying to build. So when you think about autonomous driving, there's like multiple meanings. One is what we call like level 2, level 3 driving, which is stuff like hands-off driving, where like the car will drive itself on like a highway. And then you have like things that are like level 4, level 5, which what we called is eyes off or mind off, which is essentially like you don't have to pay attention or even look at the road. So what we were building for Autopilot was kind of the level 2, level 3, which is I can go onto a highway, it will drive itself and do its thing. And the market we were targeting is for everyone else. One thing we noticed was that around 2018, 2019 is that most manufacturers are already bundling a camera in their vehicle to do things like parking assist or like automated cruise control already. And the thing that we could do is by making models that we are really good at making small, putting them into in the car and essentially running it on potato hardware, we could actually unlock all this functionality for self-driving without actually adding any hardware for the customer.
What were some challenges that you had to deal with?
You're essentially running these really complex deep learning models on potatoes. It's really hard to do. And think about the computing power was essentially like, let's say a tenth or a quarter of a Raspberry Pi. And so what we had to do is get all this data that we would collect. We would have to then transform it into something that we can train models on. And then we would train these like mega models and then shrink them down to run real time on tiny hardware.
How would you shrink them down? What were some techniques and tricks that you learned from years of practice, I imagine?
Yeah, it's interesting stuff. There's things like, first is data quality. If you are training the model on a lot of data where some of them disagree or are not consistent, the model has to be bigger to kind of like see through that. But one thing we notice is that if I actually just get data and clean it very well, you actually need less model capacity to represent your data set really well. So just really clean data was one avenue.
Sure.
The other ones were a little bit more exotic, which one of the things we did is I have a paper on this.
Yeah,
it's called
I was going to ask.
Squeeze
I knew there was going to be a paper somewhere in this story.
Yeah. No, it is. We did have to. A lot of the technology wasn't there yet, and so we had to develop a lot of it ourselves. But I had a paper called Squeeze NAS, and the idea is that we use a network assisted search to essentially find the best network for the hardware. So what we did is we used a neural network to then find the optimal network for the maximum accuracy and the lowest latency for a given hardware set, and that helped a lot.
I want to know a little bit before we move on about you became CTO of this company and you were doing the very much ML stuff. You also had that low level distributed computing aspect of it, I guess. And so when you were looking at the systems, what were some of the other pieces that you were factoring in when you were architecting these smaller models on very, very dumb or tiny, I guess the proper word is tinyML, and the half Raspberry Pi or the tenth of a Raspberry Pi? What else were you thinking about as you were deploying these onto the cars for everyone else?
Yeah, there's a lot of different things. I would say like the important thing is to think about the whole process, right? You have these models, and the thing that we were optimizing for was iteration speed. So what that means is producing new models quickly, dependent on what failures had happened. And so we think about that. One of the things we need to be able to do is produce these models quickly on these large training clusters. So we were one of the early people who did distributed training. And the thing that was really interesting there is when you start making these models smaller, you end up stress the system in weird ways. So one thing that would happen is because we're training these small models, our GPUs were running this pretty efficiently, but the amount of data you had to ingest for these models it increased exponentially. Because think about if you have like a large model, the amount of GPU to CPU work is quite balanced. But once you start shrinking that model, the CPU work doesn't go away, but the GPU work is now getting faster and faster. And so we ended up getting bottlenecked in all these weird places for training, and we had to like kind of reinvent the wheel to kind of make that work. And then it just kept on going. Like we kept on just running into weird issues. Like when it came to model deployment, what we noticed is that some of these platforms that we were targeting were invented like 10 years ago as an accelerator. And what we had to do is that if we ran it on just a CPU for this, these hardware that you put in the car, and these hardwares were, you could think of them as like these platforms that are made by like a company called Renaissance or NXP, these companies that you pretty much have never heard of, but they have a monopoly in the car computer chip space. But the thing is that sucked about them is that they're kind of designed by committee. And so they just have a bunch of random shit in there. Like they'll be like, oh, we have this one accelerator for these operations, and we have this other accelerator for these other operations. And so we ended up building a compiler to be like, okay, here's an input model, and then kind of like divvy up your model onto these other chips. So we had to do is design models that had layers that were easily mappable to multiple parts of the hardware.
Damn, so you had to do all kinds of janky shit.
Yeah, it was weird. It was weird. And then I think the worst thing we had to do is one of the vendors we worked with had a chip that the compiler was only in Windows. And that was probably like the worst month of my life.
And I'm guessing this is a lot of cutting through regulation too, or the chips were like this because they had to go through rigorous regulation red tape.
It is true. Yeah, that is the case. So typically when we talk about self-driving hardware, they have different levels of what we call ASIL. And the idea is like how safe is this chip? And so a lot of these chips have like failovers and redundancies such that like if something breaks, then it can still operating as normal.
Yeah, it makes sense. So inevitably you probably created a lot of stuff while you were there. And is that what made you see the light and realize that, hey, you know what, with this complex data stuff, there's probably a few businesses that you could create around it. I know that you did this and then you went and you had another stint in self-driving cars, right? And then you started Daft?
Yeah, it's an interesting history. So I was at this company called DeepScale, and then we actually got acquired by Tesla. And so I worked through that whole acquisition process. And after Tesla, I then went to Lyft to kind of lead a lot of their self-driving efforts around perception. And then that team got acquired by Toyota. So I worked at Toyota for a bit. And then after that, after 4 companies of essentially building complex data systems and being the builder of these systems and user of them, I was like, okay, other people need tools that I kind of I had and were great. But once you leave, you don't really have anything. And so what we wanted to do is kind of bring the functionality that you're familiar with, like a database or a data warehouse for tabular data, but to the complex domain.
So you inevitably thought deeply about if the world needs another database. What made you decide, and explain more about what you're creating with Daft?
Yeah, for sure. I guess like I'll talk a little bit about what we see as the common issue right now with if you are dealing with complex data. So if you're a company dealing with complex data, what I most often saw in the systems that I initially built were kind of bridging together the best of relational with these kind of batch processing engines. So imagine you are a self-driving company or a biotech company. You have a bunch of things like images, videos, 3D scans. What you would intuitively build to kind of build an engine end to end to process these images is getting a traditional database or data warehouse, putting all the metadata in there. And when it came to the assets, like the video or image, you would just have like a pointer to some remote storage, like S3.
Mm-hmm.
So you'd put a bunch of images in S3 and have a database with all the metadata.
Yeah.
And what would then happen is when I wanted to process this, I would have to do 3 different steps. I would first have a data analyst write a SQL query to be like, what data should I process now? Then you would run that query and you get a list of files. And then you do something like Spark to then process them and then give you the results where you then dump the S3 or dump the results back into a SQL table. Then you would finally get another data analyst to actually process the end results and give you the analytics that you cared about. And what we saw is like these really nasty systems that had to talk to 3 different teams to actually do this end to end. And I was always like, okay, first, if we're running a query, we can't optimize the end to end. And number 2, dealing with Spark with images or videos or 3D scans was like a nightmare. What would happen is that Spark doesn't have the right abstractions here to represent the data natively. And what would happen is that you would have one machine get too much memory from having all these images in memory, and it would or out of memory, and then that would die, and it would rebalance, and it would just knock out the rest of your cluster like dominoes.
Yeah.
Yeah. And I always just like killed me going through like 10,000 line log files of like Java errors and like finding what was the one line that caused my bug. So I think I could spend collectively weeks of my life on this.
So painful.
Yeah, it's so painful. And I always thought like, hey, you know what? If we had a system that was like natively understood that this is a 2 gigabyte file and don't just load it like dumbly in memory, that would make my life so much easier. So after all my stints in self-driving, I kind of talked to a few companies about like, hey, if I work here, what do you want me to work on? And 4 of the companies that I talked to out of 5 said, hey, we would want you to handle this whole side of unstructured data processing. And I was like, this sounds like a good startup idea. And then I paired up with someone I worked with at level 5, at Lyft level 5, and he was also very passionate in the space. And we started the company, Eventual. And our first product that we worked on, or we're working on, is called Daft, which is an open source query engine for all those types of data, where it understands it very intimately.
And the idea is that you can load in all of this data and then you can query it easily, and the metadata is with the unstructured images, and that is my understanding. Is that correct?
Yeah. So it's kind of like, I would say, it's a distributed data frame that's all Pythonic, but the entire engine's right now in Rust. And what it looks like to the user is something like a pandas data frame, where I can say, I'm going to read these millions of files in S3 as like read files. I want to then process them as an image. I want to crop them, resize them, and then I want to load them into a machine learning model for either inference or training. And what it looks like to you is you're just building this query using a lazy API. And when it comes to execute it, it will actually run it on a cluster using this query plan that it develops, but then also intimately understands the data it's running on. So no more errors and very optimal queries for complex data.
That's awesome. So then this is Daft. Eventual is what?
So Eventual. So we want to be a lot more than manage Daft. So what we're working on is we have users. So most of the users of Daft right now are actually in the enterprise space. So they're right now using open source Daft to do a lot of query processing of unstructured data. The question we get after, how do I run these queries on complex data or unstructured data, is how should I store it for better retrieval? So the next product that we're working on is it still will be open source, but a enterprise managed version of this, which is how do I store my data efficiently for complex data? So think of it as a complex catalog for everything unstructured.
And it differs from just that S3 bucket in what ways?
So if you're familiar with like a data warehouse or a database, you get all these amazing features like governance, like schema evolution, like time travel. But there is none of that for for example, a bucket of images in S3. And so what we're trying to do is give you the things that you're familiar with BigQuery, or Athena or large data warehouses, but for unstructured data. So think of it as, I want these teams to have these permissions, and I want to add this new column, or I want to delete this column, or I want to have a retainment policy. These are things that we're adding on top of just plain old S3. Also much faster loading. Rather than just a bunch of single images, we can actually compact it into something that's really easy to load in.
Oh yeah? How's that?
So there's some interesting formats you can do. So what we see right now is people stuffing a bunch of images in Parquet, which isn't really the best. It's great for Tabular, but isn't necessarily the best format for images. So for a lot of this, we're developing our own container formats to be able to load data really efficiently for images, or seek to certain parts of the image from cloud storage directly.
Oh, nice. So inevitably, man, I'm sure everyone is asking you about how you fit in this large language model world, and unstructured data is so hot right now. What is your thesis, or how do you look at it when it comes to whether it's whatever text to image, or text to animation, text to video, any of that, or just straight generative AI with a OpenAI call? How are you seeing what you're doing at Eventual playing into this like new paradigm of machine learning? And if at all, because maybe you're like, yeah, right now we're focusing on this slice, and it's not actually that important to us to get distracted with the shiny new toys.
Yeah, I mean, that's a good question. I would say a lot of what we're building is compatible with the future of LLMs. So some of the use cases we're working on with some of our early users are around LLMs and generative AI. So a big one is actually retrieval. And so are you familiar with like chain of thought for LLMs?
Yeah, dude, so we talked about the exhibit example earlier.
Yeah.
There's this great paper from Alex Radner and a lot of other people that I can't remember who, but he was talking about distilled step by step, and it's basically distilling the model. Have you seen that paper?
Yeah.
Okay, you know about it, but I'll explain it for the listeners in case they missed it. It's distilled step by step, basically it's distilling the models, but when they distill it through the large language model, they're asking for this chain of thought reasoning. And so it makes it much easier for you to get that distilled model and train it with less data, because the metadata is so rich from the chain of thought reasoning prompting, or chain of thought prompting, that you get from the large language model when you're creating that training data for the distilled model.
Yeah, it's super cool stuff. It's crazy to me how different distillation is now compared to distillation when we used to do it.
Back in your day?
Back in my day, distillation was like kind of dumb. Like what you would do is you would train a big model, and then you would just train essentially like you would use that output as the ground truth for a smaller model, and that was it. And then, yeah, I don't know. It was just like, maybe the big model understands the labels better than the ground truth. And then, I don't know. But anyway.
Come a long way from there. Anyway, I distracted you. Tell me about why you were talking about distillation in the first place.
Oh, yeah. So the way I think about chain of thought reasoning is it's quite compatible with this. So one of the use cases we're doing now is being able to process data like the Red Pajamas data set, being able to load it in, filter it, and then do things like tokenization, do things like run an open source model on it, and then doing things like I have a set of embeddings and I want to do this hybrid search over a large data set of find me sources of text that were published to this date, have this type of style, and then have similarity closer to this. That's kind of like the first level use case. The next level use case is actually plugging Daft straight into the LLMs and having, if I ask the LLM, hey, give me some documents that, show me, I don't know, that are written in the style of, I don't know, what's your favorite author?
Hunter Thompson.
Okay, Hunter Thompson. And so the thing is, for a lot of these models, we don't really quite have things pre-computed, and we don't necessarily know what the modal query looks like. And so what we can actually do is actually plug in Daft as one of the query sources for LLM. So think of it like, we've seen all these demos of LLMs writing SQL to then send it off to a database and retrieve it and then parse the results. We can do the exact same thing for complex data, which is have LLMs write these queries, search over these large corpuses on S3 or in these data lakes, bring back the results, and then have the LLMs interpret it.
Interesting. Wait, say that again? I'm not sure if I fully grasped what you were saying there.
Oh, what I'm trying to say is like just how we, can provide a SQL engine for LLMs today to understand some of your tabular data. We could do the exact same thing for complex data, which is I can have my data lake full of multimodal or complex data and have the LLM write Daft queries to then try to understand them better.
Oh, dude, that is awesome. Okay, I see what you're saying. So then these are some of the large language model use cases. I imagine 4 out of those 5 dentists that you talked to earlier, or whatever they were, when you went out to get a new job before starting Eventual, and they said, hey, we want you to work on this use case and this problem area. They weren't necessarily doing things with LLMs back in those days when you started Eventual. And so there's a ton of other use cases. Is it very much like where you see it soar, where you're seeing Daft really take off is in your past life kind of world where it's the self-driving car world? And I know you mentioned also drug discovery. Is that another use case area that you see it taking off?
Yeah. So the area that we see it taking off and the areas we're focusing in are essentially the domains that don't get much love. And so
Gotta love
right now,
that.
if you're trying to, And so right now, if you're trying to process images, there's a bunch of different tools that sort of work. And so for that, it's kind of crowded. But what we actually have talked to a lot of our users, if I'm trying to build a way to build queries on audio data and like read all these different audio sources, transcribe them, and then do all these different various analytics and filtering, there's not really a good tool for that. And so what we really lean into is making sure we work really well for these domains that don't get quite much love. And so that's things like audio, 3D assets, like game assets, microscopy images from biotech, which is like these large lossless images that are hard for Python libraries to typically interpret.
Yeah.
And also just weird, wacky things. Like a big use case of ours is someone sets up a Kafka stream and they dump a bunch of these protobufs in S3. And then now they're like, hey, how do I just filter over 1 billion protobufs for things that have this in their field? And Daft works great for that.
Oh, nice. Okay, so you could potentially work incredible for playing around and querying a lot of MLOps community podcasts.
That's a great use case. Like if there's like a bunch of sources or URLs for the podcast, and we can pull them in, transcribe them, chunk up the text, and then, and then find out interesting things you said, and then maybe train a model to fine tune it on your voice and replace you.
Then I don't even have to be here. I can just have you interview the fake me. Maybe I'm not even real right now, man. Who knows?
Yeah.
So that's we'll have to do some kind of hackathon on that later, because I think that would be super fun to pull all that data. And also it sounds like you're making it really easy compared to what I had thought we would have to do.
Yeah, it's really easy. I mean, you could spin it up in Colab and then get the query working, and then it's the one-line switch to switch it from running locally to running on a distributed cluster.
Nice. Oh, that's awesome. So now, what are some things that you took from your self-driving days and all this tinyML stuff that you were doing, and you're now bringing into Daft or Eventual?
Yeah, I think there's a couple of concepts that I think are really important. I think one thing that I took away early was if you focus on traditional data systems in the tabular space, the individual rows don't really matter. It's about the analytics result, right? But in complex data and self-driving, the individual rows matter.
Hey, Laszlo here. If you're serious about MLOps, you hit subscribe right now.
So it's like if I'm trying to search for failure cases, the individual results matter, not the analytic part of it. And so it's almost like you have to build a system that's like hybrid transactional analytics, but you're not really doing transactions. So one thing we built to Daft early is how do we make sure like needle in the haystack queries are really performant and easy to do.
Yeah, that makes a ton of sense. So it feels like, and this again, going back to that whole idea of the self-driving cars, it feels like, I know we mentioned it beforehand, it's one of those high risk or very high, there's a special word for it that the EU uses to classify the ML use case. I can't remember. It's something high. Damn, I can't remember. But basically, it's dangerous because there's lives that are potentially affected in very bad ways if shit goes off the rails. And so making these needle in haystack use cases or cases you're able to find them really quickly in Daft seems like, yeah, it's a no-brainer. You came from that world and now you're seeing, hey, how can I make that very useful, even if it isn't with this high danger situation?
Yeah, the needle in the haystack type queries, we see them a lot now and in the generative AI space as well, which is find me this document that exhibits XYZ. And you end up searching, like, you're not saying how many documents are there that exhibit XYZ. You're saying, give me the documents that exhibit this. And so we see this pattern quite often now where you want kind of the best of both worlds. And so we're doing that. And for the whole safety thing, it's quite interesting because I'm seeing a lot of similarities between the self-driving domain and thinking about safety and the whole LLM stuff that's happening now. Like, I would say for any AI you develop, it's important to essentially have a safety net so it can't do harm. And the way you think about how rigorous that safety net has to be is what can it do? So when you think about self-driving, what we would do is, you need a way for something to take over. And so we would have the self-driving stack. You would have a safety layer in software to prevent things like, hitting the curb or hitting a person that was outside of the traditional system that would be running for, the end-to-end automation. But then you would also have a safety driver who would take over at a second's notice. So essentially they would be, hands hovering the wheel and grab the car and disengage whenever something would happen.
Yeah.
And the way that any of these AIs are developed, including, the ones that we see now, is you have feedback loops. You essentially put something out there, you observe how it does, you see the failures, and then you improve it. Where as for self-driving, that feedback loop is very expensive because you need a human to literally constantly monitor it. So all the feedback, all the validation you're getting is supervised by a human. But for the whole Gen AI space, it's quite interesting because I put them in two domains. One domain is where it's okay to fail. And I see that in a lot of creative applications where if I'm doing copywriting or image generation.
Wow.
Yeah, exactly. Any of those, there's not really a right answer, and there's no right answer to fail. And so it's okay, right? There's as a use case where you can put out there, and the feedback you're getting from users is what images they're actually clicking and actually downloading based off what they generate. But then other domains, like let's say legal AI, is you still have that feedback loop, but then they have to be reviewed by lawyers. But each time that they're being run, it's going to improve over time. So I kind of view it analogous, but a little bit different.
Yeah. I remember the word, it's high stakes. That's what
high
they
stakes.
call.
Yeah.
Dude, I can't believe I was totally blanking on that one. So going back to what you're saying though, 100%, I fully agree with you on that, where there are these expensive feedback loops, but you also want to make sure that there is some kind of safety net just in case. And it feels like there's these use cases with generative AI where you don't need safety nets per se, because the worst that can happen is you get a deformed face on an image that you generate, or you get a copyrighted image that you generate, and you got to figure that out and make sure that you just generate something better and you become the curator and whatnot. Or when it's generating text, then you can add your flavor to it, and there's not really any high stakes there. But when it comes to more of this legal documentation, or if we're talking about, I mean, there's a few different high stakes potential here that you do need a bit of a safety net.
Yeah, agreed. Like, that's the thing I feel like it needs to be understood better. I feel like I see a lot of companies or individuals starting these projects, which I think are great, but for example, legal AI is like, I think I see a future where it works, where the lawyers are using it, but at the same time, I pay my lawyers a lot of money because they don't make mistakes.
Yeah.
Otherwise, I would just do it myself. You know what I mean?
Yeah, exactly. I know how to prompt this, whatever Harvey came out that, so I could figure that out on my own. I understand what you're saying on that, and then coming back to what you're doing with Daft and how you're thinking about that, how does that tie in?
Yeah. So a lot of these use cases, like for example, Harvey might do is they have these corpuses of legal documents, and they want to be able to get these documents, use image processing on them, extract out text, and then run them through LLMs. Those are things that Daft would be a really, really good tool. What we see right now in the generative AI space is that a lot of people are just writing Python scripts that go over each file, extract the text manually, and then hit the OpenAI API. And they kind of then dump that either in a file or like one of these vector databases. And then kind of the process completely restart once they switch the model or switch the kind of thing that they're doing. And so we want to make that really easy to do, which is I can build my entire pipeline just using a data frame like I would do for pandas. And when you're ready to commercialize it or make it production ready, you just switch a couple flags and then you can run this on a cluster. So it makes their life a lot easier is what I would say.
Yeah. Oh, dude, I see the vision then. I see and I understand that. So one thing that I also wanted to mention and bring up is, and you kind of hinted at this before, is around how you think about the needs and trade-offs when it comes to tabular data versus this unstructured or complex data, and certain things that you need in tabular data and other things that you need in complex data, and how you look at the two architectures. And if you're setting up a system right now and you only need to go down one route, maybe it's the tabular data route, then what are you going to be building for and optimizing for? And then if you have complex data, what are some things that you're keeping in mind and optimizing for?
Yeah, that's a good question. I guess like talking about the axioms of both, I think is really important. So when we talk about tabular data, you typically think like integers, floats, things like strings. And most of the time when you have this data, the queries you're running are usually aggregations. So what that means is that I have like these files of text. They could be large files of text. And what I'm essentially doing is going through each row and then doing things like min, max, sum. These very cheap operations to compute. So if you think about it as what is the volume of data I have and the volume of compute, it's actually much more data heavy. So it's like I might have gigabytes of data, but I only have, billions of operations. So they're quite balanced. But let's talk about an image. Images and things like text for LLMs is completely different. Whereas if I have like a 100 kilobyte image, I'm processing potentially trillions of operations on it. Right? Or if I have like, let's say a work of Shakespeare, which is only like a megabyte, I will be processing, quintillions of operations using an LLM. And so the ratios that we think about of compute over the data is completely different. So when you're building complex systems, you have to think about it as I will be compute bound almost every single time. Whereas like if you think about traditional query engines, you're like, okay, all they're doing is optimizing for, reading from S3 and they don't really bother about the compute. which is fair because they're going to be bottlenecked by that.
So then what are some, okay, I love you break it down by the axioms, and you think about, hey, let's look at the fundamentals of one versus the fundamentals of another and what the bottlenecks are going to be and what you're going to encounter. And so then as you're building systems around this, what are some things that you would say, I definitely want to have in my toolkit if I'm dealing with one versus the other?
Yeah. I would say if I was building an analytics engine, I would go for something simple and something that failures are handled in, in a way where we can recover easily. So for example, like if you're running things on like a Spark cluster and you it's fine because the amount of work you have to reproduce is not bad. Okay. But if you talk about that in terms of like a complex data cluster, that does not work very well. And so what we're building around that is first making sure Daft understands the data types natively. So they understand what an image is and how expensive it is to bring into memory. How expensive is it to send it around? And also for these various other formats as well. Also understanding that placement and scheduling is very important and we require really high utilization. So an example is if you get a lot of these complex data workflows and map it to something like a Spark cluster, you only use about 20% of the hardware.
Okay.
And so if you're using GPUs or, you're running LLMs or a computer vision model on this data, you're pretty much burning 5 times more money than you have to. And so some of the things that we're doing here is saying, okay, you know what? Our users are typically enterprise companies who want to save money. And by porting things into Daft, they can run things that's, Pythonic using data frames, but then still get really good utilization and cheap throughput, essentially, for their whole system. And so, yeah, the things we're designing around there, once again, are really understanding the data we're working with, having query plans that are necessarily not optimized for tabular analytics, but for complex data processing, and actually being really tied into the hardware we're running on. So really understanding the AWS machines we run on and how to get the most out of them built into the framework.
I wanted to go down one route, but then when you said that last part, it's like, I thought about something else got triggered. You have this background in tinyML, and how does that play into things? And that, like with Daft, what is it optimizing for, or how are you thinking about those kind of use cases?
It's pretty interesting. So I guess one thing I'll go into first is what's the eventual goal of Daft, right? No pun intended there. So the way that we're building out Daft is right now, although so our user interface right now is in Python, and all of the engine and stuff is a hybrid between Python and Rust. As we're building more and more, we're getting to a mode where we can run completely serverless, where you can run things in Python on your laptop, but then when it executes, it can completely run without state in a cloud cluster and then spin down as soon as it's done. And one of the difficult things with that, with models, is that most of the models right now require Python. You typically use PyTorch or TensorFlow, and you embed that into Daft or typical workloads using Python and do a bunch of this glue code. But one observation that we've noticed is that, although at the beginning we wanted to make things really easy for Python to build models and run them in Daft, we noticed that a lot of people just run the same models in Daft. Like they run the same, LLM models, they run the same computer vision models, and they might change things like weights, but the models are generally there. So one of the things that we're going to in the future, which is where my background comes in tinyML, is how do we actually embed models in Daft where we can run them, compile them down to hardware, run them on CPU or GPU natively without any Python or any framework, and then execute that very efficiently on the cluster. And so that's one of the things that we're working on, which is if I have something like a llama model, we can actually just package that as part of Daft, run it on the cluster, and there's like no work on your part you really have to do.
And then you can bring it down to the running it on a potato, as you said, and having this capability just
Yeah,
out of the box that works.
it works. And like, I think it's getting really interesting because if we think about like the inference per dollar for a lot of these models, GPUs are usually the most efficient, right? Like in terms of a cost per dollar, inference per dollar. But the problem is no one can get GPUs now. There's a massive shortage, which is stuff that I dealt with that when I was working at Lyft. We would use all the GPUs in a single data center, and we had to learn a lot about how do we do things differently so we can actually do our work. And so we're seeing that now with this whole Gen AI wave is that I'm in this Slack group for AWS support, and every day people are like, can I get more GPUs? And the guys are like, no. Right? Is that we have to start thinking about alternatives. And so what do you do if you need to get this, if you need to get your shit done and you can't get GPUs, you need to adapt.
Yeah. You have to figure out what's the way around this, and how can we make it work without the GPUs that we have been relying on this whole time. So what's the workaround?
Yeah, so I think a big one is, I mean, have you seen all this really cool work on like Llama CPP?
No. Wait, is this the one where it's just super small llama models?
Super small. So this guy essentially got Facebook's Llama model and then just wrote.
He did Whisper, and then he did, you can run it on your computer, right? Like you can run it on a CPU on your whatever laptop.
Yeah, exactly. And so what he did is like made the model smaller, so it fits better in memory, and then wrote a hyper-optimized version and purely in C++ using vectorized operations and whatnot for this one model. And so when you compile this model, you essentially just have a single binary that does the inference of the model. And I kind of see that as, the future of a lot of these LLMs, which is you can package these standardized LLMs that are optimized for your hardware as part of your query, and then use it to extract or do generation or whatever task you want.
Oh, incredible. I mean, this is making the assumption that I keep telling people, that open source models are going to be good enough. And right now they're not there. But the big assumption that everybody's saying is like, open source will be there in 6 months. Don't worry about it. It's going no matter what.
Yeah. I'm big on open source. Like our whole company is on open source. I think open source will take. I mean, I see a lot of analogs that computer vision was. So I started doing computer vision in like 2012, and during that time, the big bad computer vision algorithms were all in companies. You had companies like Clarify, you had Google, you had like Apple. They were doing all this crazy computer vision, but then you would have these open source research papers come out, and then they would be a little bit better, and then the companies would surpass them. And then we got to a point where people just kind of stopped caring because the open source was just so good. And now what people do is they just use them as a black box for their tasks. And that's kind of what we see now for computer vision.
Yeah. I mean, I hope it is like that. Don't get me wrong. I am a huge proponent of the open source world doing its thing and optimizing it and making it free and open, of course. We haven't seen it yet, and a few of these attempts, I try and play around with them, and I'm like, dude, this isn't 6 months behind. This is like 2 years behind.
I would agree with that. Like, it's probably going to be more like years, like 1 to 2, 3 years rather than months. Because the moat here, once again, is like a big cluster to train these models on. Like if you have a huge cluster where you can train these models on, then I think you can do it. But to get to the base level, I think the next part is then making these fine-tuned data sets of like Q&A, like OpenAI has done.
Yeah. 100%.
I'm excited for it though. I'm a big proponent of open source, and I think it will take off.
Awesome. Sammy, this has been fascinating, man. I love talking to you about all of this, the history of where you've came from, where you're going, what you're doing. Last question I have for you is, over the years, you have inevitably succeeded on a few things, you've failed on a few things. Where do you feel like you succeeded where others typically have failed, and why do you think you succeeded?
That's a good question. I I feel like it's because I care about things that people told me not to care about.
Oh,
And I
how
think the
so?
biggest one is when I started my career is that the advice I got from a lot of software engineers was, oh, don't worry about making this run fast, or don't worry about going low level. It's not worth it. And the advice I got from them came from an era when, computers kept on just getting faster when you do no work. So you can write shitty software and computers will just get faster, and then your code will be no longer an issue. Or the other thing they would say is that, oh yeah, computers are much cheaper than software engineers, right? But then I would always put my optimizer hat on and go into the assembly or go into the low level and actually just really understand why things were running the way that they did. And so at DeepScale, like that ended up paying off. And at Lyft and Toyota, that ended up paying off. And now I feel like that experience is really getting there, which is understanding why things are slow or why things are fast, because I did not listen to the advice people gave me in the beginning of my career.
Incredible. Man, this has been so cool. Thank you so much for coming on here. I think we'll end it there.
Yeah, thanks for having me. It's been a great time.
Hey everyone, my name is Aparna, founder of Arise, and the best way to stay up to date with MLOps is by subscribing to this podcast.